This is One Universe at a Time. I'm Brian Koberlein. Scientists cannot deny how useful mathematics can be in proving their hypotheses and establishing credibility for their work. But is math just a means to an end, or could it be considered a form of science unto itself? On today's program, Dr. Matt Hoffman, an assistant professor of mathematics at the Rochester Institute of Technology, will grapple with this question and explain how even mathematicians can disagree on the answer. In the context of mathematics, one of the things that often comes up is a discussion about whether or not mathematics is a science or whether or not it's a tool that's used for science.
The question is who it comes up with, where that's a relevant question and what it's relevant for. But if we want to have a discussion about what it actually means, I think we need to start probably with what we're defining these things as. So, I guess I want to ask you what you think science is if we're going to have this conversation about it.
It's interesting. I would say, on a broad sense, science is about models that describe reality.
So you're putting reality in there, and that's one of the places where you will see math dinged as not being a science. You make these models that have nothing to do with reality, although sometimes they do come back and of course,
bite us.
Now we get into the metaphysics of what reality is. If you're seeing it in the numbers, is there some universal truth in the numbers that mathematics is describing?
Right.
Even if it's not the natural world, right? I think the natural world is something that has been attached to science, probably, that dominates a lot of the discussion about whether math is going to be a science or not.
Right. The simple philosophical view that a lot of scientists might use is reality is whatever kicks back.
Yeah, and I think it also gets sort of science uses the scientific method. So there are these things with the scientific method that then get placed into the discussion. I think Gauss said, math was the queen of the sciences a long time ago.
Physicists would say physics is the only true science. Everything else is stamp collecting.
Yes, physicists would say that. And, mathematicians would say, well, you really need us to even have this conversation. One of the interesting things that comes up with describing it as a science is you can try to parse the words, but a lot of the time it becomes an identity to the people who are doing it. Mm-hmm. And depending on the person and what their interest is, they might have a different take on this, right? There's you're saying physicist has this identity of, oh, no, we're the true science, right? There's that XKCD comic where you're talking about the purity of science, and it's,
you've got sociology, and then physics is saying, yeah, we're the pure ones, and mathematicians are saying, why are you guys over there?
Yeah, I can't hear you guys, I'm all the way over here, and a lot of mathematicians will wear this as a badge of honor, and I think that's an interesting aspect of it is, if you asked mathematicians whether they think it's a science, you're going to get their discussions colored by whether they want to be listed as a science, whether we want to associate with all of you dirty scientists and your unclean data, data is unclean and messy, and you don't have any absolutes. And in mathematics, we like absolutes. And I think actually that becomes one of the real distinctions if you want to really try to parse it out.
And in physics, we take a kind of a different approach, is that the experiment is the ultimate educator of truth, as it were. And if you're not going to be doing that, then you might as well be doing philosophy.
So far as physicists and truth are concerned, I think your frictionless spherical cow has something to say about that, or at least it would have something to say if it weren't sitting in a vacuum. There's definitely a lot of approximations that get made in here, and the question of where you're talking about reality and where you're not, I think, can get pretty fuzzy. But I think if you want to talk about math as a science, really, in terms of the definition, personally, I kind of don't like trying to say it's not, because you then get into the discussion of what is math. But as someone who associates as an applied mathematician, and it's something that comes up in a lot of math departments throughout the world, as to how you are defining math now that applied mathematics is a bigger thing.
Well, and I think part of it, too, is that a lot of people, I think part of the vast majority of people who are not going to be mathematicians, in some sense see mathematics as a tool because that's how they're taught it. If you're going to be an engineer, if you're going to be a chemist or a physicist, then you have to take these math classes in order to do the real stuff, quote unquote.
Yeah. A lot of people, and I think not incorrectly, would say mathematics is the language of science, which I think is very apt in many ways, but I think occasionally does a disservice in that it can also be used, I feel like, to trivialize what's done in mathematics. Because you say, whatever, you're the language of math, but let us now take everything that you've done and use it to do real things that are important. Right. You're doing go play with your language.
Go play with your blackboard and we'll get to the real stuff.
You're worried, and your students have this attitude because they get worried about, this is just a really technical point. This is punctuation. It's not important to me because I'm going to use it to do something bigger. And the fact that this comma is missing, and that's really all you're complaining about, is not a big deal in the big picture.
Well, and in fairness, we do that. I mean, our engineering students taking physics often have the same approach. Physics is just a tool to be able to do the real stuff, which is engineering.
I guess you guys would have that too. And I'm sure any English majors would point out the importance of commas and
right.
But that is something that I think is true in terms of talking about a language, but also when you're classifying it in that way, I think there's some drawbacks that I don't like seeing. Part of the reason why I sort of hesitate to say it's not a science, even though as I think probably if you want to technically classify it, maybe you would say it's not, is that I think it's sort of misunderstood how close the process in mathematics is to science in terms of the scientific method process. Now, the big, because you've got this process of observing something, and whether you're talking about looking in the real world versus looking at patterns in the numbers or in whatever set of axioms you have, you're looking at this and you're coming up with patterns. You're seeing things. Oh, I think this could be true, right? Mm-hmm. You make a hypothesis, right? You come up with a theorem, and then you try to prove it. And I think mathematicians, we like propagating this stereotype of being very smart and very sort of, oh, yes, this is true and this is why, right?
Right, the brilliant genius.
Right, yeah, the brilliant genius. And there's a lot of the sort of mathematical identity, I think, for a lot of people that actually likes cultivating that.
Yes, mathematics, that's really hard. I could never do that.
It's really hard.
You're right. No, you couldn't.
No, and also, right, there is this moment of genius sort of thing where you're looking at something that is the way a lot of it works. And I think a lot of people who go into math throughout their careers as students, right, this is one of the things that's attractive. It's like a puzzle in many ways to people where, and you can be looking at a really hard problem and you're looking at it and all of a sudden you're in the shower or you're sleeping and, and all of a sudden you wake up and, aha! Right?
Eureka!
I figured it out. Yeah, exactly. And oftentimes that's what it takes, right? I mean, that is, you've been sort of slamming your head into a wall and then all of a sudden you have an insight that you didn't have. But making that sort of the glamorization of the process sort of obscures the struggle that goes on there and all of the sort of not experimentation in the way a physicist would say it necessarily, although maybe some theoretical physicists, but all the sort of struggle, I think, is a lot of the experimentation. You come up with a theorem, right? You try to figure out the right way to approach it. You try a number of things. Some will work, some won't, and eventually, you'll come up with something that will allow you to say either yes or no to your theorem, right? There's the sort of differences would then be whether you're using experiments and data, right, which is typically something that people would ascribe to science, right? And then you've got the other issue, which is the level of proof between mathematics and science. And that's a big one in many ways from a technical perspective, because in science, a lot of the time you look at enough data and you make predictions, and if your data bears those out, you will feel good about it, but you're not going to claim to know truth.
Right.
Or
we would never say that something is now no longer up for debate.
Exactly.
And in mathematics, you would.
In mathematics, you would.
And
in
in
fact,
proof. This is not up for debate anymore.
Yes. And in mathematics, that's exactly what you're looking for, is this. It works for everything.
2 + 2 is 4.
Yeah. In some ways, they're both the same in that you're trying to get to prove for as many cases as possible, right? It's just with math, you want that to prove that as the limit goes to infinity, then that
right.
That
you want to have
holds.
all possible theorems covered from
exactly.
your initial postulates. So that's the scientific aspect.
Yeah, but I think just saying math's not a science does a disservice to the actual process that happens when you're doing math. That it's actually a very similar way of thinking. It's just that the experiments aren't quite the same type of experiments that you would think. The easiest explained unsolved mathematical conjecture is the Goldbach conjecture, which is that all even numbers greater than 2 can be expressed as the sum of 2 primes. Right. So it's very simple to say.
Very difficult to prove.
Very difficult to prove, right? No one has proved it. But people have, say, done what I would consider sort of experiments in that you can certainly test a whole bunch of numbers.
Run it in a computer and start going.
Well, right. Yeah. So if you can do a bunch by hand, certainly, 6 is 3 + 3, 8 is 5 + 3. So you can imagine, it works for those, right? You can now plug it into a computer. You can run it. I think they verified it for up to something like numbers of order 10 to the 18th, I think. It's something along the lines of that, right? So there is, I would say, a lot of experimental evidence that this is
probably
good.
True.
Probably true, right? Mathematically, we would say it's unproven, but still this process, right, that people are working on this, they're working on this very mathematical concept. I mean, this is certainly not I was looking out the window the other day and I saw that all numbers are going to be the sum of two primes, right? So it's certainly not what you would consider traditional natural observation, but it's sort of an observation from looking at, oh, hey, look at all these numbers. This is something that seems to work, right? So it has this aspect of what I would consider more traditional science, and the process in terms of experimentation, sort of numerical simulation in some ways, you could almost think of it, is similar to the way most scientists would go about it. But there's this difference of, we're waiting for absolute proof before we can say it's true. Right. And that might be the real sticking point.
Whatever the consequences of the mathematics turns out to be is going to have consequences for the predictions of physical theories. So the Riemann hypothesis, for example, is one that shows up in string theory and quantum gravity and things like that. We don't have a proof for the Riemann hypothesis.
We do not.
And so whatever direction that goes, and it is very abstract and
that's a much more difficult thing to explain. I'm not even going to try to explain that. I don't want to do that.
But in terms of that, there are kind of physicists waiting to see what the outcome of that is, because it's going to affect what the physics turns out to be.
Sometimes you approach a problem specifically because there is a natural phenomenon you're trying to explain, and sometimes you're doing something, but then it turns out it actually applies to something else, right? I mean, the Riemann hypothesis,
is one of these kind of abstract
there's now a lot of things that come about that actually this is relevant to, but that wasn't necessarily the reason why people started looking at it in the first place.
Right, and I think that's something that you see a lot of in mathematics, where what we would think of as being just kind of pure mathematics, go off into the field and examine your own navel mathematically, comes back to bite us. It comes back to hit reality again. You know, I mean, the famous one is Riemann. When you had Euclidean geometry, the idea that everything was flat and lines were parallel or not, and then Riemann went off on this abstract curved space thing, and that's nice. It's nice.
That's cute. Nice work.
And then we get to relativity, and it's oh golly, that actually is a physical now theory that we need Riemann mathematics and Riemann geometry in order to do physics now.
Yeah, one of my colleagues has a cartoon on his door that says all math is applied eventually.
That's actually pretty good.
So the other thing I want to say when I first heard this conversation is that I brought this up to a few people, including my colleague Paul Wanger, and his response was to invoke the great Bryce Harper of the Washington Nationals and say, that's a clown question, bro. In some sense, like, why do we really care? Why is it really important to make this distinction? And I didn't know when you were thinking of this question, what was sort of the distinction that
I think for me as a physicist, it's very easy for me to lock into the idea of mathematics as a tool. And I know it's more subtle than that, but just kind of on a basic level, I do think of physics and models and experimentation is what makes a scientific theory, which mathematics seems to lack. And I know that's a common view of physicists.
Yeah, that's fair. I guess I worried that the classification sometimes, it does a disservice, and especially as we get sort of farther and farther along, it seems like many more of the fields sort of blur together.
On a kind of a separate thing, I know one of the discussions that's in mathematics is whether it's independent of physics or not.
Yes.
Does it depend on reality, or is it separate from the universe?
Well, I think there's certainly there's part of the scientific method, right, that has to do with falsifiability, like whether it can be falsified or not. And so, you've got theoretical physicists like string theorists, right, that are running into this, are we still doing physics? Because
deeply so. There's a deep argument about that.
Yeah, and we have a numerical relativity group in our math department here at RIT. Yeah. So there's a lot of overlap. And I would say, I'm going to guess that physicists probably sometimes would joke with each other disparagingly about being a mathematician, not a physicist, and mathematicians the other way would make fun of each other for saying you're not a mathematician, you're a physicist.
People will always, the other departments are more comical than we are.
Yes,
we are the true science.
And we feel the same way, right? You don't belong here. Go hang out with those other people.
Right. And a lot of it, I think, it really is the categorization. That in some sense, I'm a physicist, not a mathematician, in part because I have a physics degree and I'm in a physics department. And you're a mathematician, in part because you're in the math department. And so it depends on what department you're in. We have that with chemistry. Is material science physics or chemistry? It depends on who's doing it.
Right.
Is environmental science, is it chemistry, is it physics, is it mathematics?
Yeah.
Depends on your department.
And when you're teaching it, somehow it makes a difference. When you get into meeting other professors, you actually find out that a large portion of them are professors in things that they didn't study.
Right.
I know a lot of oceanographers who were electrical engineers,
right.
or mathematicians who became oceanographers. That wasn't what they studied, and I think it works
you get a lot
that
of
way.
crossover.
There's a lot of crossover.
Right.
So at a certain point, what you end up doing is maybe not necessarily what you learned, or maybe actually, to put it another way, maybe what you learned applies to a lot of different fields, and it's hard exactly to categorize one, put them in nice discrete bins.
You're listening to One Universe at a Time. I'm your host, Brian Koberlein. We've been talking with Dr. Matt Hoffman, Assistant Professor of Mathematics at RIT, about whether or not math is a science. In the second half of our show, Dr. Hoffman has a few questions to ask me. He wants to know the difference between a scientific theory and a law.
So after the discussion we just had about definitions, I wanted to ask you one that comes up a lot in physics, and that is, how do we distinguish between what we consider a law and what we consider a theory?
I think the typical view is that a law is somehow bigger than a theory. That you go kind of from a model or a hypothesis to a theory to a law, and the law becomes the absolute truth. And in reality, a law is just simply an observed relationship.
I almost feel like the theory in some ways becomes bigger than the law, that actually that's sort of the other way around.
The scientific theory would be a stronger claim than a law.
Yeah.
A law is just simply, this happens, don't know why. So if you look at Kepler's laws, for example, planets move in ellipses. Why? They do. I don't know, but they do. We observe this and we can follow that.
Right.
The law of gravity is things fall. Near the Earth, they fall at 9.8 meters per second squared. Why? No idea. Whereas a theory is actually a construct that connects ideas and observations.
So in some ways, a law is the part of a theory that is sort of nice for marketing purposes. You have a nice relationship, a nice sort of soundbite that comes out.
Yeah, I think it's a simple rule that we see observationally, and it's not necessarily always true. If you say, for example, there's things for a spring. The more you stretch a spring, the more it will pull back on you, and it's called Hooke's law.
Yes.
Hooke's law is a thing that some materials obey to within certain limits, but some materials do not. It is not an absolute truth.
Right. Well, gravity works this way too, right?
Gravity works this way too, yeah. Or Kepler's laws or anything like that. If we say the law of gravity, we have this rate of fall, but it's not exactly 9.8 meters per second squared.
Right.
And
depending on the scale, it might or may not work. But it doesn't sound nearly as good to say the law of gravity when we're in a space
with
that's sort of not really too small or too big.
Right,
yeah.
Right.
Who decides what becomes a law and what becomes a theory? Because it seems some ways that there are things that I might consider a law that would be a theory or a theory that they're a law. And
I think it comes from a kind of bastardized history of science, and that we tend to categorize things because they were useful, and then we tend to rewrite our idea of history to match. Kepler's law is a really good example of that one, because we kind of portray it as, Kepler came up with these rules, and they were laws, and that was perfectly acceptable. And then we found Newton, who then expanded it.
Right.
But that's not actually what happened. What actually happened was these ideas were already there before Kepler. And when Kepler kind of synthesized them, they were nice rules, but they weren't called laws until after Newton.
Okay, so originally it was
1800s.
Kepler's theory.
Or just Kepler's model. I'm not sure exactly historically what it was called, but there was still controversy about, it's a nice trick, it's a calculating tool, it's a mathematical tool that you can use, but it doesn't explain anything in the context other than, well, it allows us to calculate what the motions of the planets are.
So there is this transition then that happens from considering something a model or a theory to then graduating to being called a law.
And we have laws that we call laws, but we know they're not true. Bode's law, for example, for the distance of the planets, was a rule that came up. It became known as Bode's law. We know it's nonsense. It's just numerology, but it is something that's still called a law.
There's not really any universal standards. There's no governing body that makes this distinction.
There's no official body of scientific law that
stamped.
Says, it's a, now you're a bill.
Yeah. It's just sort of something that happens in the general consciousness somehow. It gets talked about, and someone writes a paper and they call this a law, and a bunch of people cite that paper and continue calling it a law.
Right, and I think within the historical context of things, that when we tell the story of science is when we often start introducing these, I think, things as laws, because we like to tell a very clean story of science, that some genius discovered this, and then some other genius discovered this. And it's never like that. It's always this collaboration of a lot of people pushing back and forth.
And it's also probably useful from a pedagogical perspective, too, to be able to tell students, this Newton's law.
Yes, first A.
Learn it, right? Or in my textbook. Here are the laws. This is your study guide.
Right.
You should know all of the laws.
Right. Memorize these and know how to calculate
Where it's
them.
harder to say, understand gravitational theory.
Right.
Go. This is your homework.
Derive theory from first principles.
Yeah, exactly. Like that's a harder thing to do. But I think it is sometimes confusing to me as a mathematician scientist, whatever we decided in the first segment, and I'm sure much more to people who aren't in the sort of scientific field, to sort of think about which is actually a bigger deal, right? That this sort of law has this connotation as being more important, and in some ways you normally think about things graduating to a law.
Right.
But the theory in some way is actually what's explaining what's actually happening, and it sort of encompasses more of the topic.
Well, and I think in some sense we use law in different ways. So we'll say something like the law of gravity, and we know that it's a relationship. But when we say something like the laws of physics, that usually means however the universe actually works, whether they're known or not.
Yeah. So the hidden equations.
The hidden
somewhere.
equations, right. The hidden equations behind the universe. And so the theories are an approach to get closer and closer to the true laws of physics, as opposed to, well, here's a relationship that we call a law.
In some sense, a law sort of has to be written in mathematical language. So that's sort of the general way you would like to talk about.
You have some relationship between quantities, and that would be a mathematical relation.
So this idea of a theory or a law, do things get sort of upgraded or downgraded, right? So getting downgraded from a theory makes you a hypothesis again, or just not true in some sense? I mean, but do things go sort of up and back, or are they sort of stay there? You said that some laws are known to be untrue, but they still are called laws.
Right. Well, I think the terms in terms of specific laws, they just have a certain context on what we call them. In terms of theories, it's kind of interesting because, we have the idea of just a theory.
Right.
Something's an idea, or what we would kind of call a hypothesis.
Yes.
And then you have a theory that then gets proven wrong. And this is one of the arguments that come up, is that, well, scientists shouldn't say that's the way it is. It's the way it might be, because you might be wrong.
Yeah.
And of course, every scientist would say, well, yeah, the theory of gravity or the theory of evolution might be wrong. But when we talk about a scientific theory, we have a lot of evidence to back that up. There's a confluence of evidence that makes it a very robust theory.
Yeah.
And I think one of the things that gets pushed to the side is the idea that even if we come up with a better theory, the theory that we've had before works just as well as it always did.
Right.
And the Newton to Einstein is a really good example of that, because you have Newton's theory of gravity. And we know, on some sense, that's wrong. Einstein proved it wrong. It's incomplete. So we've come up with a better theory of Einstein's gravity. But at the same time, Newton's theory of gravity works as well as it ever did in Newton's time. Everything that Newton claimed about it and could confirm observationally is still true. And in fact, when we do things like calculating the motions of satellites to send them out to the planets, we don't use Einstein, we use Newton, because we don't need the precision of Einstein.
Right.
Newton's good enough.
Yeah.
And so...
when the satellites are orbiting, we do need Einstein.
And this is one of those
sort
things
of a transition.
That's interesting about how a lot of, particularly in physics, we focus a lot on models, and we will pull different aspects of models when they're useful. So, for example, the satellites, the GPS satellites, for example, going around, we use Newton's laws of gravity to describe their orbits, because that's good enough. Yeah. When we do the timing of these satellites to calculate the positions, we have to account for the time dilation and relativity. Yeah. So we're using Newton's models for their motion, and then Einstein's model for their timing, and then we're using quantum mechanics to calculate the clock measurements.
Yeah.
And so all of these are kind of incompatible models in some sense. But for this regime, this works, and for this regime, that works, and so we put them all together.
And it's a matter of the precision that you need to do it properly.
And that's the real key, is particularly in terms of applied physics, where you're looking at, you have to come up with the things that work.
Right. And there is empirical evidence that supports everything that is being put forward in terms of the hypothesis for it to be a theory.
The kind of common statement is that any physical theory will live or die based on the evidence.
Right.
That the most beautiful theory can be killed or eliminated or thrown out by actual data that disproves it.
I think the sort of term theory is sort of confusing because we've had enough. It gets used so much in slightly other contexts where there's not as much evidence, right? You watch enough crime shows or things like that. It's always
I have this theory.
This murder happened. I have a theory about what happened, right? There's no real evidence behind this or anything. Although maybe eventually, if they're doing the crime scene show properly, there will be. But
zoom in and
but that's sort of the way you sort of think about it, and so that I think it sometimes does a disservice to the science because people tend to sort of latch on to, this is a theory,
right? Or it's just a theory.
It's just a theory. And it could be wrong, right?
Right, which is true. I mean, and that's an important aspect of science, is to recognize that any of our theories could in fact be wrong. Right. And we have to be willing to accept that evidence may disprove them.
Yes.
But at the same
time, you have to be willing to accept that there is a lot of evidence that supports.
Right. I mean, flying in a plane, for example, is supported by just a theory of aerodynamics.
Yes.
And that theory could be wrong, but I bet you're willing to bet your life on it.
Yeah.
I bet you're willing to bet your kid's life on it, because we have this confirmed.
Right.
So being a theory is not a bad thing.
Do you think this is something that, as a scientific community, people need to do a better job of sort of conveying this distinction? I mean, does it get lost somehow? Do we sort of take it for granted?
I think that's part of the problem. I mean, I think part of it is that we don't do a good job in explaining, I guess in some sense, the odds.
Right.
In that we have theories that are accurate to the limits of certain observations. It doesn't mean that they're perfect, but in a very real and practical sense, they don't have to be perfect.
Right.
We can say, for all intents and purposes, this is true.
Yeah.
Now, that may become something different down the line, but we can count on this because we know that it makes accurate models, it predicts accurate results. It relates to a lot of things in science when we talk about something like climate change or vaccines that are very controversial for some people, when you can say, well, how far do you have to go when you know?
Right.
And Phil Plait just did a recent one where talking about a meteor impact. Mm-hmm. If you had a big meteor coming towards Earth and 95% of astronomers said it's going to hit Earth and it's going to wipe out a city, we would probably want to do something about it.
Yeah.
And we wouldn't argue about, but 5% say that it won't. But the experts are saying that it is. If you take climate change and 95% of the experts are saying this is actually true, do we ignore them or do we actually listen to them?
And this is something, I mean, I've heard people speak. Yale has a Center for Climate Communication. Mm-hmm. And one of the things I've heard them say is that the biggest thing that you can convey to people about climate change is that there is strong scientific consensus, that it is 97% scientific consensus.
Right.
That's sort of, if people hear that, they understand the percentages a little bit better and they feel more confident in it.
We've been talking with Dr. Matt Hoffman, an assistant professor of mathematics at the Rochester Institute of Technology. Our program is produced at RIT by Mark Gillespie with support from the RIT College of Science. I'm your host, Brian Koberlein. Thanks for listening to One Universe at a Time.